Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 32. It's on the magnetic field of a wire. Scientists for years and years and years knew there was some link between magnetism and electricity, but they couldn't find it. There were a lot of clues that pointed in that direction. If you take two magnets, let them go, north goes to south, just like positive goes to negative. If you pull them apart, there is a force between the two, and that force gets greater the closer those two magnets get together. It's just like charges. There's an attraction between the two, and actually Coulomb's law applies to both magnetic fields and magnetic forces and electric fields. What they also knew is that magnetic fields are created and can be measured using a compass. So if you take a bar magnet like this and move a compass around it, you can see that it's lining up with that magnetic field. And so what they wondered is maybe if we take a compass and move it next to a charged object, as we move it around that charged object, it's going to point towards the charged object, but it simply didn't. And so it didn't seem like charges were producing any kind of a magnetic field. And then a brilliant Danish scientist named Hans Christian Ørsted moved the charge. And so what he's got here is a current. So we've got a current, or we know now that it's electrons that are moving, but the conventional current's going to be in this direction. And so what he found is that as the current moved through the wire, it actually deflected a compass. So that particle, that charged particle, has to be moving. And so we could demo this in a science lab. Imagine if we have a wire coming out of a table and we just put a bunch of compasses around it. And so we've got the wire coming out of the table. It's coming towards us. And then we've just lined a bunch of compasses up, but we haven't turned on the current. Watch what happens when we turn on the current in that wire. You can see that we're creating a magnetic field around the wire, and we could measure that and where it is. And so if you have a wire that's a straight wire, so not a curved wire, and it has a current flowing through it, then we're going to have a magnetic field that goes around that wire. And we can measure the magnitude of that magnetic field, and it's really based on two things. The first one is going to be the amount of charge, and so how much current we have that's moving through that wire, and there's a direct relationship between the two. The more flow there is, the more magnitude we're going to have in the magnetic field. And then we have the radius, or the distance from the wire. And so again, this wire is in cross section, and so this would be the radius, or the distance away from that wire. And so there's an inverse relationship from that. The greater the radius is, the smaller that magnetic field is going to be. Now, how do you figure out which way the magnetic field is going to be? Well, the direction is going to be determined by the right-hand rule. And so what you use is your hand again, but the thumb is going to show where the current is moving, and then the curling of your hands like this are going to show you where that magnetic field is. And so in this case, I know the magnetic field is going from the left to the right. I can see that on my diagram right here. And so is the current flowing towards me or away? If I hold my thumb like this, it's coming towards me. So it's coming through the wire at us like that. And so scientists, again, figured out that a magnet is going to generate a magnetic field. And so in this PHET simulation, what I'm doing is moving the compass around the bar magnet. And you can see now the south end of the compass is pointed towards the north end of the bar magnet. But as we move it around to this side, now it's the north end of the compass pointing at the south end.
What? What? Oh, you want to know why this battery and cell wire is in the magnetic kit. Did you know that electricity can also create magnetism? You don't believe me? Okay, take that wire and roll it over a nail. Now tie both ends of this wire to both sides of the battery cell. Take a few paper pins near this nail. See, paper pins are being attracted to the nail. This is called an electromagnet. This magnetic effect comes due to electricity. So when you run an electric current into a wire, it creates a magnetic field, making the wire an electromagnet. The difference between an electromagnet and a regular magnet is that you can increase or decrease the power of the magnet by controlling the supply of electric current. If you increase the amount of current, it becomes more powerful. Similarly, if you decrease the power, it becomes less powerful. So you can control the power of magnetism in an electromagnet. Electromagnets are used in many appliances like the refrigerator, fans, doorbells, etc. And they help make our life easier. Okay now, bye!